Hey, welcome back. Let's continue now with the reaction of ethers. We are going to start with the preparation of ethers. After that, we are going to continue with the main reaction of ethers. And in a separate video, we are going to talk about, in the next video after this one, about epoxides, because they have similar reaction with others, but due to the ring strain, they have some other properties that I want to separate them in a separate video. Okay? So let's dive into the preparation and reaction of ethers. The most commonly known way to prepare ethers is the Williamson synthesis. How does it work? We start from an alcohol, we treat it with a strong base, usually sodium hydride, in THF solvent, tetrahydrofuran, that is a well-known commonly used solvent, and first we yield an alkoxide. After that, this alkoxide serves as a nucleophile and react with a primary mostly and some secondary alkyl halides through SN2 mechanism. And you know, with SN2 we need primary substrates to work best. So in this case you're going to have a purely SN2 reaction and you're going to form the ethers, right? If you want to name it, ethyl cyclohexyl ether. Okay? It works only with primary and secondary halides, but preferably with primary halides to give a pure SN2 reactions. If you try with tertiary halides, instead of yielding an ether, you are going to have E2 elimination and formation of alkenes, totally different product. So be careful. Williamson synthesis works best with primary alkyl halides. But can we synthesize more bulky substituted ethers with other method? Yes. Let's move to the next one. Next one is similar with alkenes. Alkoxymercuration of alkenes according to Markovnikov rule. So if we start from an alkene, we treat that with mercury trifluoroacetate, a typical compound, and if we react that with a secondary alcohol in this case, and demercurate that with sodium borohydrate, you are going to yield a bulky substituted ether that is not possible to be done with the Williamson synthesis. So let's see the final product. The idea is that this is going to connect here, okay? According to Markovnikov, to the more substituted carbon. That's the point. So the final product . Right, this is the final product. We can yield a bulky substituted ether. Let's move now to another example. If we start with this primary benzylic alcohol in this case, we can yield an ether both ways, with Williamson synthesis, but also with alkoxymercuration demercuration synthesis. So in both scenarios, here you have to form alkoxide, here works according to the Markovnikov rule, you're going to have the same product. So you can use either method that you have in your lab, or in your exam you can choose whatever you want. Let's move now to the reaction of ethers. Acid cleavage through HBr or HI, not with hydrochloric acid. Be careful, those two works best. This one does not do the cleavage that we want. We have two possible scenarios. The first scenario is that you have a tertiary carbon and the mechanism goes according to SN1 and E1, mostly SN1 mechanism. And in this case, you're going to have the formation of a tertiary halide plus the alcohol that remain. This is according to SN1, and some goes according to E1, and you are going to have formation of a double bond, right? This is according to SN1, this is according to E1. But if you have a less substituted ether, treat that with HBr or HI, you're going to have according to SN2 mechanism. In this case, the formation of the primary halide is the product, so CH3CH2Br plus the alcohol, secondary alcohol. Right, so what is the difference now to acid cleavage? To break it, the reagent is the same, but the mechanism to the bulky ethers is SN1. So the halide goes to the more substituted carbon. In the case of less substituted ethers, so in this case you're going to have the formation of the primary halide. Hope you get that. The second reaction of ethers is Claisen rearrangement, specific to allyl-aryl ethers and allyl-vinyl ethers. Up until now, that from an alcohol you can treat with a strong base, form an alkoxide, and after that you can react that with primary halide and yield an ether. And if you treat that at 250 degrees Celsius with temperature, you're going to have a rearrangement and the formation of this compound. This is going to attack here, this is going to move here, and this is going to move here, and the final product is going to be this one. Right? So you're going to have the formation of this product. The same thing happens with because this is allyl ether. So allyl is this group here. Aryl is considered this group here, and ether due to the oxygen here. And this one here is allyl-vinyl ether. So in this case, this is going to give this compound as an aldehyde. Okay? Not so much to remember this thing, but the first one, it was important. Thank you so much for watching, and look forward to see you in the next video, that is the reaction of epoxide. Peace!